Hello. Today we'll discuss about numerical techniques to find the approximate roots of a polynomial equation. So to do these things, we're going to use the Regula Falsi method. So in this method, one can consider a graph, a function which is plotted in this graph. So here we have plotted the x-axis, the variable one, and here we are plotting the function one. So the nature of the function looks something like this. Now here for the certain values of x, you have positive part. So this part is positive, whereas lower one is negative. This side is negative. So it's obviously our roots is lying in between the initial value of a and b. So the first job of this method is to find the interval where the function is changing from the positive value to negative value, or from negative value to positive. Now one can consider these 2 points and one can connect these 2 points by a straight line, which is called the chord. Now if you know the equation of this chord, and one can see that for certain point of this initial position, for the certain point, one can draw this chord. It starts from point A to point B. So it intersects somewhere here with the variable part. So this is our first approximate root value of this function. Now one can write the equation of this chord of this straight line. So the equation of the chord is given by y. This is equal to m into x. M is the slope part and this is the x. But as y equal to mx is from a straight line passing through origin, but here every time you will not get a straight line which is always passing through origin or having a nature parallel to this. So one can write a very generalized chord equation for this system. So we can rewrite this equation as y minus f of a. Y is the general form of the equation and f of a is the function value at point A. So y minus fa, this is equal to the slope value, fb minus fa divided by b minus a. So this factor gives the slope of the system, multiplied with x minus. This is the equation of the chord. Now we need to consider a point where the function value is equal to 0. So for certain value of x, so here in this graph, it shows that for x is equal to x1, the function value becomes 0. So this will give us the solution point where the function is equal to 0. So what we are assuming, for a certain value of x, the y value is equal to 0. So one can consider this y is equal to 0 and one can find what is the value of x over here. Just by using a simple algebra, one can find what is the value of x. So this will give you the approximate root. Then again, if you want to increase the accuracy, then again you can consider this one. So now your value will vary, your interval will vary from A to say point T. Now again, you need to go for a straight line, a chord, write the equation, and for a certain value of x, the function will be equal to 0. So again, put y is equal to 0 and try to find what is the value of x. So increase the number of iteration, or if you run the process for number of times, number of iterations, one can get a higher accurate value of the roots. Let me just check how to calculate this. So when y is equal to 0, one can just consider y is equal to 0 and you have this expression, something like this. So after simplification, one can find the value of x is equal to a fb minus b fa divided by fb minus a of b. So go for the iteration and you can find the accurate value, more accurate value of the root. Let me just check it by using a simple online calculator. So here we are going to use a Regula Falsi method online calculator. So now first you have to enter the function. We are assuming a simplest function. Here you have considered this is equal to x square plus twice of x minus of y. This is the function value f x or y you want to consider. This is equal to f of x. Now we need to check for which values the function changes from positive to negative. So this will be our interval. So in between this interval, the root of the function will lie. So just checked it that for x is equal to 1 and for x is equal to 2, the function value changes from positive to negative. So obviously our interval can be considered as 1, 2. Now actually this will be considered as a and b. So one can calculate what is the root value. So root value, just check what is the formula for this. A fb minus b fa divided by fb minus fa. So 1 and 2, this is the interval. So first what you have to do, you have to find what is the value of f of 1. Also you have to calculate what is f of 2. Let me just check what is f of 1. F of 1 is 1 plus of 2 minus 5. And here this is 2. 2 means 2 square 4 plus 4 minus 5. So this is 8 minus 5. This is 3. So this is positive. And what about for 1? F of 1. So this is 1 plus 2. 3 minus 5. This is minus of 2. So FB and FA it changes from positive to negative. Now, what is our formula? X is equal to A of FB, A of FB minus B of F into A divided by FB minus F of. Just check it. What is the formula here? Now, put these values here in this equation. So x will be, x is, so A is 1 into F of B. F of B means F of 2 in this case. This is 3 minus. So B, here B is 2 and F of A which is minus of divided by FB minus FA. So what is FB? This is minus of minus. So what it gives? This is 5, 3 plus 2, 5, and this is 3 minus, and this minus will give you plus. So this is 3 plus 4, 7 by 5. So 5, this is 2.0 and 4. Okay, so let me just check it what our online calculator is giving. So for the first iteration with a certain approximation or high level of approximation, it is observed that the root value comes around 1.4. So what our calculator value gives? So the calculated value gives, for the interval 1 and 2, the Regula Falsi gives us a root value of 1.6. Now again we can repeat this. So what we're going to repeat? So now we need to know what is the function value for the calculated root. It was calculated as minus 0.2 something. So obviously it will vary. Now our next interval will be within the positive part and negative part. So earlier one was in between 1 and 2. It was in between 1 and 2. So 1 gives us a negative value and 2 gives us a positive value. But now it root comes somewhere around 1.4. It is somewhere 1.4. And the function value is negative. So our next interval will be in between 1.4 and 2. Our next interval will be 1.4 to 2. Same steps will be repeated for the calculation of the root. Let me just check it. After number of iteration, here we have considered 6 number of iteration. So after 6 number of iteration, the root value comes around 1.44948. So one can go for higher iteration and you can get a very accurate value of the root. So one can try it for another section. It's a quadratic equation. So we have calculated it for one root only. You can try it for the other. So this is one of the simplest method by which one can calculate the root of a simple polynomial. Now we'll move to our next part of calculation or next method of calculation. This is known as Newton Raphson. So in this case also one can find the roots of a equation, of a polynomial equation with a very high accuracy. So here what you have to do, one can just think about, have a function, say f of x. Okay. Now one can expand this function in a form of a Taylor series. So if you have a Taylor series, so f of x can be written as f of x plus of h. This is equal to f of x plus h, first order derivative f dash x divided by 1 factorial. Then what we can do? We can consider h square divided by 2 factorial. And you have second order derivative and you can go for higher orders. But here, if you approximate the root, if you approximate the series, one can calculate that Newton Raphson from this. So what we have, we are assuming that the function f(x plus h) is equal to 0. This gives the root value. So one can write f of x plus of h, where when x is equal to x of 0, just consider a certain value of x. So f of x0, so it becomes x0 plus h. This is equal to f of x0, h, first order derivative x0, and one can consider the higher order terms. Now we can neglect this, and we are assuming for this condition you are finding the roots. This gives us a root. So if you are considering only these two terms, so one can write f of x0 plus h, first order derivative, this is equal to 0. So one can simply calculate what is the value of h. So h is equal to minus f of x0 f dash x. Now what is h? H is simply considered as a function. One can just think about you are trying to plot a function x and fx over there. Y is equal to fx. Now you can consider certain values. Say somewhere here you have x0, then you have x1, then one can write x2, x3, x4 up to a certain value of x. Now these values x0, x1, x2 and x3, they are equal spaced, and the space between the interval is given by h. So h is a constant and fixed for a particular function when you are solving. So one can simply write that x1, we have just solved it, we have just got it function for x equal to 0. We just consider the function at x is equal to x0. Now what is x1? Just as you have mentioned, the step size is h, the interval is h. So one can write x1 is equal to x0 plus. Same way, one can just think about x2. Can be written as x1 plus h, or this can be written as x0 plus. So one can just go for a generalized section. Xn is equal to xn minus 1 plus of h, a generalized. So now you know what is h. Okay, h is equal to minus of f by first order. So just simply write this equation. So we have considered x1 is equal to x0 plus h. Just calculated what is h. So this equation can be written as x0, the value of h. One can put the value of h. So what is h? H is equal to minus of x0 divided by x dash. Now you can go for number of iteration and one can find a very accurate value of the roots. So this is for x1. So we have just assumed that our initial guess is x0. So one can just consider the initial guess is x0. We are assuming that our root of the particular polynomial function is near to x0. Now we are going to approximate by using the Taylor series, by using the concept of f of x0 plus h. So our next, after first iteration, we are just approximating our root, a higher approximation, that x1 is equal to x0 plus h, and then by putting the value of h, one can find what is the approximated value of h. Then you can repeat the steps. You can go for iteration. From x1 to we can make it x2. So what is x2? x2 is equal to x0 plus twice of h, or this is equal to x1 plus h. So you know the value of x1, then put the value of h and you can get what is x2. Okay, that's this equation. So you have x1. So same way you can calculate for x2, x3 and up to x in minus 1. So what is the generalized form of this equation? General form of the root. This is equal to xn plus 1. Xn plus 1. This is equal to xn minus, this is a factor of h, which is given as minus f divided by, where with our initial guess, with our the function value at the initial guess. Okay. So let me just check it, how we are calculating roots by Newton Raphson method. Again, we are using Newton Raphson method of online calculator. Same function was taken, x square plus 2x minus 5 over 8. And we are assuming the initial guess is 1. So one can go for other initial values. You can start with 2. So finally you will see it is converging. Okay. So you can go for 3, or you can take minus 1, minus 2, and you can go for it. And what we are assuming, the number of iteration is 10 in this case. So now you have. So it is observed that the initial guess is very good. So within only 3 iteration, you have the converged value of this. And it gives us 1.449490. It is very close to the Regula Falsi calculation. In Regula Falsi calculation, this was 1.449. Okay. So with these two methods, one can solve the polynomial, one can find the roots of the polynomial. So let me just recapitulate the thing and then go to finish. So in Regula Falsi, we are assuming that when function is changing from positive to negative within a certain given interval, so one can draw a chord connecting this positive and negative function value. And we are assuming in between this, you have the solution. So for that case, for the certain value of x, the function value is equal to 0. So y is equal to 0. So then after simplification, one can find the value of x over there. So this is the approximate root value which gives us the function, the solution of the function. And in case of Newton Raphson method, we are using the Taylor theorem, the Taylor series. So it is observed that with the initial value of x is equal to x0, the h value, so this can be written as f of x0 plus h as f of x0 plus h first order derivative of the function at x is equal to 0. by neglecting the higher order terms, one can find the value of the interval h, which is a user-defined thing. Then one can find our next approximation, which is x1 is equal to x0 plus h, where the h value is minus of f divided by. You can generalize this root. You can go for number of iteration. So one can write the roots. The Newton Raphson formula is f of xn plus 1. This is equal to xn, which is the initial case for that particular iteration, minus f divided by. Now, the problem with Newton Raphson, or some of the advantages are there and some of the disadvantages. So the most important part is that it converges very quickly, what we have already seen. We have considered 10 steps, but within 3 steps it was converged. And it was quite efficient for calculating this thing. And in case of bisection method or in Newton Raphson method, you need to think about the interval. But here we don't need to think about interval. You can have an initial guess and you have the calculation. But there are some disadvantages of this. So obviously, if your initial guess is not correct, so you may not be converging. You may not be get a very accurate value of the function, root value of the function. So the sensitivity of the initial guess is one of the disadvantage of Newton Raphson method. But one can go for number of iterations. So one can have a iteration, one can have a convergence of this thing. So towards the root. Okay, thank you.